I actually went in and asked Joe and Alan how they would like to be introduced, and Alan was very quick in saying, "Oh, we're two old guys who've been around for a while." And to which Joe, very helpfully interjects, "Yes, we are the ones who helped create the mess we're in."
Of course, he's much younger.
And this is where a quote from Sir Tony Hoare, who was on this very stage this time last year, came up, and it was that Algol was a great improvement on its successor. And I think it's people who've helped us get to where we are today who will have a very good insight into telling us where we actually are today, and not where we who use this technology believe we are. And in a way, this is a theme of what this conference is all about, and this is the perfect way to wrap up. So I'll leave it over to Alan, who will give us an insight.
Oh, hello, Joe. How are you?
There's a movie.
That was such a hit, maybe we should quit now.
I mean, it's one of the best movies ever.
Okay, so Joe asked me to spend 15 minutes, and I will try, and maybe somebody can help me. He wanted me to spend 15 minutes to say where we were all wrong, but that is a much longer talk. So what I thought I would do is to go back into the past and show a couple of ideas that I witnessed. This is not a talk about my ideas, but some ideas I witnessed that had a big effect on me. I think many of them were very important, and a surprising number of them have not found their way into computing today. And this is partly because, let's face it, computing is a kind of a pop culture, meaning it's not that interested in the past. So, for instance, we've had even some Nobel Prize winners among the Turing Award winners. Most people here, I doubt, how many people here have ever read Herb Simon's Sciences of the Artificial? Okay, I rest my case. Now, 35 years ago, the question I would ask the audience that was coming to a talk on computing is I wanted everybody to hold up the computers they have with them right now. And they couldn't do it. Now I don't ask that question anymore because at least things have gotten a little bit smaller. Okay, so this is the fortune teller from Thornton Wilder's play. In a carnival, you put a quarter in, and if you ask her for a fortune, she will predict the future for you, but she can't predict the past. And talking about the past is hard because there are so many details. Great thing about the future is you can eliminate all the details and ignore all the difficulties. So it's the best place to be. The present is even worse than the past because it's so vivid. So it's impinging on our nervous system. So if you want to think about anything at all, you have to escape the present. So the world's greatest computer designer, Bob Barton, liked Goethe, and this is his favorite Goethe quote: "We should all share in the excitement of discovery without vain attempts to claim priority." And this is a good statement about especially how an engineering field with some tinges of science does things. There are just a lot of contributors. So we can look at some of the really great ideas. We can talk about a few of the people who early articulated them, but it's not worthwhile trying to figure out exactly who did what when. My version of this is no one knows more to his research community than I do. That was really true. Virtually every idea I had was extremely derivative in the sense of they came as reactions to ideas that were already around. Now, when we cooked this thing up, I mentioned to Joe that it happened that just about 50 years ago today was when I left what I thought temporarily, molecular biology and pure math, to take a year off and get a master's degree in computing. And I did that by accidentally showing up at the University of Utah, not knowing that it was one of the ARPA research places. And I walked into the head of the department's office, Dave Evans, and before he would give you an office, he would give you a copy of this to read, the Sketchpad thesis, which was just about 3 years old. So this is in November '66, and this had just been done a few years before, and I'd never seen anything like this, despite the fact that I put myself through undergraduate school as a systems programmer for the National Atmospheric Research Center, programming supercomputers. So I could program, but I didn't know anything. Does that sound familiar? I thought I knew something until I stumbled into this place. Saw this, well, this was the invention of modern interactive computer graphics, user interfaces, direct manipulation, a whole host of things, what Ivan called masters and instances. We'd call them classes and instances today. And instead of programming in an imperative form or even a functional form, you programmed in Sketchpad by telling the system relationships that you must have solved. So this system actually solved problems in real time, and if I had more time in this talk, I'd show you the movie, but it's available online. You should look at it, because this is not only perhaps the greatest PhD thesis in our field, it also, many of the things in it compare favorably to stuff that is being done today. This thing was just completely out of sight. And then because the latest graduate student gets the latest dirty task, mine was to get Algol going for the university computer. And it turned out it wasn't Algol, it was the first version of Simula that had been put on top as a preprocessor to an Algol compiler written in machine code. And we actually learned about this system by unrolling the listings down the aisle of the... It's an interesting interface if you think about it. If you have a 100, 200-foot-long engineering building, you can run a lot of code down there, and you can get a couple of graduate students to crawl on it, and you can call out to each other. Hard to do with modern things. And this was a procedural system. Their insight was, what's really interesting about Algol is almost nothing except the Algol block. An Algol block is a thing that had a bunch of variables. So it had a place to store state, and it had a main routine. The variables could have procedures on it. And they thought of this thing as an entity for computing. And so one of the things they had to do was to get rid of the Algol stack so that they could have many, many blocks around at the same time. And so what they called classes and instances, activities and processes. So to them, an instance was not a static thing that was thought of being more data-like, but it was actually something in process. And whereas Sketchpad had this beautiful relational constraint programming, Simula required you to program in procedural form, but what was cool about their not quite objects was that you could hide really ugly stuff inside their not quite objects, and the objects would look nice from the outside. And so wanting to do this, you wind up thinking about, well, maybe I can do more than I can do over here if I'm careful. And like I said, I had a degree in molecular biology and another one in pure math. And so those separate entities, independently in process, reminded me of cells, and also reminded me of time-shared virtual machine processes, because that's the first thing you do when you have a computer is you make virtual machines out of that computer so you can run protected computations. And That reminded me of computers on a network, which the ARPA community was just starting to think about doing the ARPANET as the prelude to the internet. And all of these things had this simple bus structure of nodes on a bus and any object here being able to communicate with any other object. And of course, if I wanted to simulate those biological cells, I'd make up something abstractly like that. And so here's something we all know. It's one of the first things we learn about computers. I knew it also, but I didn't really know it. I knew it in a useless way. But seeing this, I started understanding it in a much better way. Yes, you can't go lower than a computer if you want to do arbitrary things. So going to data structures is meaningless. You can't go lower. Going to procedures, it's meaningless. So I started thinking about, yeah, I don't want to go any lower than a computer. And what was the problem? Well, the problem is that, especially the time-shared virtual machine processes like Unix, the overhead for each process was about 2K bytes. And what that meant was you couldn't simulate the number 3 with a Unix process and get away with it for too long, particularly with the memory sizes back then. So there was an engineering problem here. And then the other thing is if you think about scaling, and this is what biology is partly good for. We tend to think on the scales that we live in computing, but biology is on scales millions and millions, billions of times larger. And once you scale out, as we were thinking about in the internet, you have to get away from gear-like meshing of procedure calls and stuff, and you have to go to something like messaging. So this is just simple stuff here. And the other cool thing about tissues is they all have the same DNA. So we have about 250 different kinds of tissues in our body, but there's one class object, if you want. There's one thing that every one of these things holds, and every special thing that each one of these tissue cells can do is not a new thing. It's something that is actually comes out of the organism itself. And my math major was in algebras. It's one of my old books that I had to use. And the cool thing, there are many cool things about vector spaces, but one of the ways of looking at it is what you're trying to do in algebras is to emphasize the similarities over the differences to get generic things that are powerful and worth proving things about. That's the whole point here. And so I started thinking about what I call generic messages back then. And then a little later, I met Marvin Minsky, was a hugely impressive guy. On the strength of that, I got this book. I commend this to you. This is one of my top 10 books, I believe, in technical fields in the 20th century. Hardly read at all in computing because it's actually about old-style computing. It was a class he wound up teaching. It was basically 50s computing of finite automata and the roots of computation. But boy, no book was written more beautifully. Every part of this book, it's just absolutely beautiful. And I got a glow from it. And one of the cool things he did in there was when he was trying to explain what Gödel did. Instead of doing the Gödel way of representing simples using powers of primes, he made a Lisp. Powers of primes, it makes a perfect computer memory. So why not put cons pairs in there? And he made a whole little Lisp language in there. I'd never seen Lisp before. And I learned Lisp in this really weird way. It was just so goddamn neat. I was talking to David Turner earlier. Is it just, boy, when you can do it that neat, you have an urge to do the rest of the stuff that neat. And that got me to look at an earlier book that he'd done where basically his students' PhD theses. I commend this book to you just for the fun of it, because the way I looked at AI back then, just as a biologist, I didn't think they were going to get to AI anytime soon. Well, philosophically, I think it's definitely a possible thing. But what I went batshit over in AI is they were the only people in computing that were worrying about meaning. Everybody else was worrying about how to make simple little machines and debug those simple little machines, where the AI people were interested in systems that not only could hold larger meanings, but also could reflect on those meanings. And in that, because Minsky had mentioned McCarthy, the last couple of chapters in this book are one of McCarthy's earliest papers called Programs with Common Sense. And I don't want to take too much time here, but you must read this paper. This is 1958, conference over here in England, and a lot of people that Joe knew were also at. McCarthy was the guy who made up the term artificial intelligence. And he partly made it up because he had looked at a Sage air defense terminal in the 50s, big thing with a guy with a gun to point at things on that, still around in our aviation support system. McCarthy looked at those and he said every house is going to have one of these. And he didn't worry about personal computing or anything, because what he thought, the thing that occurred to him, this is like getting your power from the outside. This is like getting your water from the outside. It's going to be a utility. It'll be a universal utility, be like the telephone. Everybody will have one of these things, and there will be national computing centers that everybody can tap into. And he started thinking about it, and he realized, oh, the problem is nobody can deal with computers on the computer's terms. We need a common sense way of dealing with computation. And so he proposed that there be an agent called the advice taker that you could have back and forth with, and not just ask it questions, but tell it things and have it reason. And there's a whole bunch of interesting stuff in there. So what I got from this is the future, and if you think about it, if you're going to get this stuff around to everybody, the future has to have common sense interfaces. The one we did at Park, the GUI, was also a common sense interface because it mimicked much of what people knew about the world and didn't try to explain how machine code worked. And the other thing, which I think is a more important one for the conversation we have later, is that the future has to be some form of relational advising. We just cannot continue to survive by making very complicated machines by hand. And in fact, nature doesn't. Once you get into biology, completely different set of dynamics rules. And also in this book is a paper that had just gotten written as a memo, and this is one I want to say just something about, because McCarthy wanted everything. He was a really good mathematician, so he thought about things that way, which means relationally. And he thought about things in terms of having some sense of what it means to make a deduction or an inference. But he wanted, this had to be a robot, because it had to take on new knowledge, so it had to reason differently in the future than it was reasoning now. That got him thinking about robots in general. And the problem is, if a robot can be in Philadelphia on Monday and in New York on Tuesday, that defeats normal predicate calculus, because you have two facts that contradict each other. And so this paper called Situations, Actions, and Causal Laws should be of great interest to Erlangers. So a situation for McCarthy was the set of states in a world that are consistent with each other at a particular time. We're not going to worry about anything except what he called a situation. And we advance things by getting to the next stable situation. And he wanted to do that by deductive inferential means. And so he hit on a great idea. Too bad we don't use it very much today. And that is, to every piece of what we'd call data or a fact, he added the timestamp of the situation this fact was valid in. Got it? Right? So this is labeled, the labeled states idea. What this means is you can go from situation 3 to situation 4 by purely functional means. You don't need monads. You don't need any of that stuff because it is exactly like what tail recursion in Lisp does for you. Tail recursion gives you the effect of evaluating all the values you're going to use in the next frame and then doing the effect of a simultaneous assignment. And that next frame you've walked into is a situation that is bound, but it doesn't have to be, by a stack discipline. Think about that. So Strachey, by the way, one of the great computer scientists the UK has had, grabbed onto this. Landon grabbed onto it. And the sad thing was, from the US standpoint, is people over here understood this much, much better, partly because they were better in math. So this paper is really interesting to look at. And we use it in computing in a few isolated areas. We use it for transactions on databases, right? Because we absolutely do not want to munge databases. But basically, for most programming, various kinds of logical brinksmanships are done to try and deal with the fact that functions are nice, but you need to advance the state of the system over time. And McCarthy, early on, had a good way of looking at that. Well, that got me to look at, so simulate time along with process. Basically, just don't let the CPU be your clock. And in between, McCarthy had written this paper in 1959, which is the paper on Lisp. And he did Lisp because he wanted a programming language for the advice taker. Isn't that great? So he thought of the application, the big application. I want to do an artificially intelligent agent to deal with time-sharing interaction. And I better invent a language to do that. So one way of thinking about it, what I took away from this, it's all about dynamic meanings, not static meanings. And these meanings can be negotiated. It is not remotely like programming in Fortran or C or C++ or any of that crap. And then, just quickly, the other thing that was going on in many different ways was trying to make things happen by matching patterns and doing transitions. So I'll just mention Ingvi in 1958, a system called Comet for doing natural language parsing. One of my favorite, have you seen that?
I was going to ask you a question about this paper.
Well, yeah, I love this.
Dan Ingalls said, if you read that paper,
It's
a month of your life will vanish, and it did.
Yeah.
Because I implemented that.
Yeah, everybody does. It's a test.
Did I pass or fail?
Yeah, you passed. No, but this is kind of a test for
I
graduate
was looking
students.
at that 10 minutes ago.
I love this. This is just, and it was done on an 8K byte, 6-bit bytes, 1401.
Yeah. So I was going to ask you about Ometa and Meta 2.
Yes, yes. So this is just a beautiful thing. It's basically, the earliest thing of what is called PEGs today, programmable grammars. And there's just a lot of, this is it in its own language. That is all there is to make itself. It's so freaking cool, isn't it?
It is. It's about, Dan Ingalls told me about it.
Yeah, so.
He told me not to read it. Because if I read it, I would stop what I was working on, and
Yeah.
in fact, a month of my life would vanish, and it was completely true.
What's cool about this is besides this in here, he also has the definitions of 2 other languages. He has a small algol and a fairly large algol. This paper is only about 8 pages long with a couple of, it's just the greatest little thing. And the thing that's great about this is this is where the rubber hits the road, because it is kind of the perfect compromise between all the theoretical stuff you might want to think about and what it actually means in some pragmatic thing. Hey, all I want to do is write a translator. I loved it because it was so efficient that you could think of it as an active interface language on objects. That isn't the way Val thought about it. Then IMP is worthwhile looking at, January 1970, of the communications of ACM, because Irons was the guy who invented the syntax-directed compiler, and his interest was in doing languages where the procedural headers were actually the grammar of the syntax for that particular procedure. So you extended, when you wrote a procedure, you got to decide whether to use some standard way of doing it or extending the language, adding a new kind of control structure in there. That work was mainly done in 1968, and then the amazing planner language, which was really the affected Prolog, even though the Prolog people say no, but it did. And so 2 big hits out of the many here shows how messages can be parsed on the fly. It's just so cool. And Planner was powerful enough so its matching and the way you did matching could actually do negotiation. And to me, as a biologist, doing something the size that the internet was going to be, you can't know exactly what you're going to call something at the other end of the internet. So there's going to have to be a looser binding where meanings are negotiated, just the way programmers would negotiate. And so I love this just because, and there are many reasons I loved it. And then just quickly, Moore's Law. This is Moore's original public paper in Electronics, 1965. Lead to such wonders as home computers, automatic controls for automobiles, personal portable communications equipment. Electronic wristwatch needs only a display to be feasible today, et cetera, et cetera. So, and because anybody who can deal in this domain, and by the way, back in the old days, you had to be good at both hardware and software to get a degree in the ARPA community. It just wouldn't let you out if you couldn't do both. But once you know enough physics to understand his argument, you start seeing what the possibilities are. So here's something not made with hardly integrated circuits, 1962. But it was the first personal computer, and that box to the left-hand side is where all the electronics is, right? So, but this computer is a wonder. It was interactive. It had many wonderful things about it. You programmed it in a kind of an assembler, but it was a late-bound assembler. These ideas, the advent of a 512-bit ROM got me to do this machine for my thesis. So a desktop computer with a tablet and Windows and an object-oriented operating system. And there I used some of the Irons ideas and some of the Meta 2 ideas, and the hardware emulated bytecodes. And meeting Seymour Papert and looking at kids, I didn't want kids tied to a desk, so I started thinking about the further future. And yep, Moore's Law allows one of these things to happen, I thought, by at least 1998, and that was well within the bounds of it. And this one had quite a bit of blue sky stuff. I wanted the objects to have a planner interface because I wanted the kids to be able to do AI and deduction as part of their programming, and blah, 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 blah. So this is the easy part. At Park, we got to actually build it. So translate this, the Dynabook, into the interim Dynabook, bonk, bonk. All of 128K bytes. We used half of it for the display. So just to take you into some realm that you may never have thought about operating it. What would it be like to do a complete Macintosh kind of interface, where you only have 64K bytes to compute in? That's what we had. And the interest here is that Smalltalk 72 was nowhere like what we wanted. But it actually would be completely understandable to people who know Erlang and the actor languages. Completely understandable, because it had this idea of an interface grammar. It did parse the messages coming in and so forth. Okay? So one way of thinking about when we get down to here, reality is often inconvenient, particularly to a person who's more of a scientist than an engineer. On the other hand, it's illuminating and useful sometimes because you actually get something that you can do things with. And these trade-offs are the things that you have to keep alive. When you do something, there's a tendency to be proud of it. And the truth is, you can only be proud of the fact that you did it. You should never be proud of the thing. Okay, and last set of ideas here. By the time software engineering of a language gets in good shape, the language has become obsolete in its level of needed expressiveness. Does that sound familiar to anybody? I mean, this is the bitch of it. It is not that it's easy to design a good language. There are thousands of languages that prove it's hard to design a good language. But man, it is really hard to make a good language run fast enough to be generally useful. And by the time you've slaved away on all of this stuff, things have moved. As Butler Lamson used to point out, he was probably our greatest operating system designer in the US, a Turing Award winner, did many things. He said, look, the problem is it takes minimum 3 years to do an operating system. And by the time you have it done and successfully going, the actual design rules have changed from Moore's law. The kinds of memories, the trade-offs in memories, the kind of memory architecture you can do. So every time you start off, you're starting off with much less knowledge than you normally have in engineering. So one of the ways of thinking about it is the best languages of an era should be the assembly code for the next languages. And so here's assembly. I shouldn't put Algol and Fortran in there. That is really disservice to me, they're kind of the same, but Algol was really significant. Fortran is amazing for its ability to optimize itself in its day. Now, this picture is ruined by Sketchpad, where Ivan just jumped into the future we haven't gotten to yet by eliminating the bad kinds of coding we do even when we're being good. Because he went to something where you're programming basically in terms of requirements. And if you think about that, boy, if we could program in terms of requirements and we could debug the requirements, we would have something like what other engineering disciplines have in a serious CAD system, a serious simulation of the CAD designs, and a serious fab facility to deal with the real problems of doing programming. Ivan sort of just jumped there. Because Ivan was a great programmer, did Sketchpad in 1 year by himself, but he didn't care about it. He absolutely didn't care about it. What he wanted was to do something that would allow people who are designing complex things like bridges and cars and linkages and everything else to just sit down and think through the design aspects and try them out. So Lisp came about roughly at the same time as Fortran, a little bit after, but of higher language. Simula really was built on top of Algol, almost, and Strausstrup made C++ specifically to be like what Simula did with Algol. He said in his first paper, I want to do a preprocessor for C that does to C what Simula did to Algol, and that's what C++ is. Lisp spawned Planner, and Smalltalk, maybe it was an unholy combination of a bunch of ideas, but we were not trying to be particularly original. We were just trying to be as clean as we could. And actors came out of that. Now I'm going to leave, Prolog came sort of there. Prolog is complicated because I just really don't like programming languages you can't make an operating system. No, come on. You've got to be serious about programming. But I do like some of the little programming. Prolog has a couple of things that would be nice to have in a much stronger way. For instance, concurrent Prolog by Shapiro solves many of the semantic problems that Prolog has. Then I'm going to draw the line here for the purpose of ending this talk, but point out two fun things to me happened in the mid-'80s. One of them was Linda, and the other one was Erlang. I remember first seeing Erlang and thinking, oh, God. You know, and I didn't worry about whether it was like Smalltalk 72 or not, because it's totally irrelevant. The thing was, they had a good set of problems that required independent objects to be relatively protected against each other and shitloads of them running. And the system had to be fault tolerant. And once you have those things, you're either going to do a really terrible job, or in the Erlang case, it got the thinking to what I thought was of a level that was worth it in the 80s. The 80s had more resources, particularly as far as memory, and it made thinking the Erlang thought. So I thought that was really good. The Linda thing I really liked, not because of Linda, but because of the idea behind Linda. And I'm sure people have looked at it here. So for instance, if you squint at Linda the right way, you will see something like Meta 2. Because you get, and if you did Linda better, you would be making a kind of system for making transactions between processes. That's really cool. And if you look at the second order version of it, you wind up with something like Prolog, right? Because Linda matching is incredibly rudimentary compared to what the matching actually could be. It could be doing a lot more. And so, yay for Erlang. It kept on going, and somehow Gerlernter couldn't get people to pay attention to what was good about Linda. And so what we should talk about is maybe what should Erlang be an assembly code for. But since you're running it now, you can talk about anything you want.
Yeah, cool. I think the term interview was wrong. It should have been a conversation, I think.
Sure.
Because
we'll have to remember
I should tell you the story of how Erlang came about. I was using Smalltalk, and I never actually got through this boundary of sort of assimilating the class structure in my head so that I could program it. So I found it rather painful. So I used to use the changelog to find things, and I grepped it and found that. And it was on a Sun workstation, and it was so slow that I'd take a coffee break. And while it was garbage collecting, I'd go and drink coffee. And I ordered the first Tektronix Smalltalk machine. And while I was waiting for it, I thought there's no point in programming Smalltalk because it's so slow. But I built an object model. Well, really, I built a model of communicating processes. The object model, I was just drawing bubbles on the blackboard with arrows. And these were I wasn't thinking in classes and methods. These were messages. They were flying all over the system. That was the problem I was interested in. And then a guy called Roger Scargaval said, do you know Prolog? Because I made an algebra to describe this. I said, no, I don't know Prolog. So he took me in his office and he said, look at this. This algebra you've made is a Prolog program. You just move a few brackets. And I went, oh, my God. And from that moment on, I wasn't interested in Smalltalk anymore.
Yeah. Well,
and I got this Prolog
neither
system.
was I. But
and I got this Prolog system, and I thought, yeah, let's do a message passing object model there. And the other influence was CSP, because I'd read Tony Hoare's CSP. So I wanted kind of Prolog, message passing, and CSP. I didn't know about actors at all. Then I met Carl Hewitt, and he said, well, did you know about actors? No, didn't know about that. But
I
when I learned about it later, I thought, yeah, we were having exactly the same ideas.
I think CSP was too rigid.
Yes, I think so.
That was its big problem. It was too gear-like and not enough biology-like. But yeah.
And then I thought, hang on, I'm going to ask you a few questions. I was scribbling around here, and I got these notes, and I don't have to ask you. You've already answered them yourself by talking about Meta 2 and things. And I was going to ask you about Meta and this stuff, but we might get onto that. But so now I'll go back to the start where I wanted to start, and that was the idea of this was about 3 years ago. I heard you were going to give a keynote at Strangeloop. And somebody told me that. You didn't.
It didn't happen. No,
it didn't happen, but at the time, so I mailed Alex Miller and said, I'd like to talk to you on stage, because our paths had sort of virtually crossed, but not physically crossed. And I thought it'd be just nice to talk to you. And I thought maybe a few thousand people might want to fit in and listen to this. And the reason for that was actually an interview or a conversation that Jules Holland had with Elton John. So Jules Holland had this late night with Jules Holland, and he was interviewing Elton John. Now, both are pianists. And the nature of this interview was completely different to the nature of a normal interview with Elton John, because the first question Jules Holland asked Elton John was, I hear you were highly influenced by somebody who nobody's ever heard of.
Well, he went to the Royal Academy.
Yeah, and
he was a pretty good
and Elton
piano
John just sort of lit up like a candle and said, "Oh, you're
Yeah.
somebody's asking me sensible questions for once." So I was going to start off by asking
Okay,
you
so
about
this will
Van
be a
Chore's
test on your
paper.
first question.
I thought this would have the same effect, but you then preempted this by.
Well, that's the job of any good talk.
So the other thing I thought, I was wondering if you were the modern embodiment of Balthazar Gracian. Because he was this 17th century Jesuit monk who was a master of the aphorism. And he wrote these books of aphorisms. I don't know if you've ever read them, but you certainly should read the Perilous Wisdom for Practical Wisdom for Perilous Times and the Art of Worldly Wisdom. I mean,
Yeah.
they're brilliant.
I'll confess, not in French, but
No, and what Gracian did, he was the master of the aphorism. And I think you're the modern embodiment
Well, I'll
of
tell
that.
you-
Because the nice thing about these short, pithy quotes is, I rather like Twitter because you strip away all the nonsense. If you've got a quote that's a few characters, a couple of sentences long, 20 words long.
well, so let me.
It reduces the thing to its core.
Yeah, I think it's something that seems better until you examine it more closely.
Well, it's something like a Zen
So
koan.
I-
You can
well, I-
mull over it and discuss its deeper
Yeah,
meaning.
so it turns out I don't think about things in terms of those quotes at all. And I'm basically a paragraph and page guy rather than a sentence guy. And I'd never had to worry about compressed communications until I went to Xerox and we had periodic visits from Xerox executives of
So-
one kind or another. And in the middle of a 3-day meeting early on there, I realized these guys were not actually even able to remember 5 sentences in a row. That is, because they were basically reactors. They're reactive types. And so I thought, my God, these people think in terms of slogans. I'd better start making some up. And so I started. And not the first, but one of the first was the best way to predict the future is to invent it, which was more or less yelled at the Xerox planners in 1971 because they were worrying way too much about what Univac and IBM were doing. They wanted to know about trends, and we said, bullshit on trends. We're not into trends here. We want to do personal computing and worldwide networks. We're just going to do it. But in fact, in our attempts to explain this to them over the first couple of days, it made no effect. So
I think there are several quotes I would call them bonk you in the head quotes.
Sure.
Because when you hear them, they boom. Why didn't I think of that? And they
yeah,
they have a truth
you
to
can
them.
if you spend some
So
time.
I'm gonna. So
I don't just come up with them. I think
you think about it very carefully.
Damn
yes.
right I do. It's
So
the
one of my
hardest
favourite
writing.
ones.
Short writing is the hardest writing
It's
there
very
is.
difficult. So one I liked a lot, and I tried out on the Ericsson management because I just loved it so much. And it said, if you don't fail at least 90% of the time, you're not aiming high enough.
Yeah.
And I thought that was really nice.
It is. And
So do you fail 90% of the time?
of course not.
95%?
No.
99%?
No, the important thing about, these things are gestures. Once you go into slogan land, you've gone into fiction, you've gone into theater, you've gone into gestures, you've gone in. My wife is a writer, and she has a zillion books on writing. My favorite one has the title, How to Tell Lies for Fun and Profit.
Oh, I've got that as well.
It's a great book.
It is, it's brilliant.
True, truly great book. And so the thing is that, in our world, we can only lie to the computer by being stupid. That is, we make stupid things that are consistent. but we wind up getting a kind of consistency that is not really aspired to or even thought about in the outside world. In the outside world, the theatrical world, what you're trying to do is get them to pay attention at all. And I got this from a book by Neil Postman. A guy wrote Amusing Ourselves to Death and The Disappearance of Childhood. I commend his books to you. And he and I became friends, and I found out that when he was a grad student, he used to travel around with McLuhan just to see what McLuhan would do. He and another graduate student. McLuhan didn't sleep. So very often, the two graduate students, McLuhan would be in bed in his dressing gown and smoking a big cigar, and the two graduate students would be there and McLuhan would just talk and talk and talk and talk. And they said one of the things they noticed was that when McLuhan was up on stage, if somebody asked him a question or somebody argued with him, he didn't bother answering. He would say, well, how about this one? He'd come out with another one of these McLuhan Zen koans. He wanted the master of making these things, McLuhan. And Neil said at some point, he and his friend realized, McLuhan actually doesn't care whether people agree with him or not. What he cares about is whether people are paying attention at all. That's what his goal was when he was on stage, was to just get people to even register it because they're thinking about other things. And being in an audience is a tough thing if nobody's getting killed on stage. It's tough. And so McLuhan had evolved this thing that is going beyond slogans and beyond aphorisms to things that are paradoxical because he wanted you to think about them again.
So one thing I'm thinking is that there's this kind of, what I get, I've listened to some things you get.
Failing 90%, it's bullshit.
And I've had this bonk you on the head moment. I'm wondering why.
But for, failing 50% of the time, it just doesn't have any punch in slogan land.
Right.
So you have to exaggerate because you're going into a low-pass filter.
Well, yes, because I was in an Ericsson management meeting, and I quoted
that's
this.
The typical low-pass filter is a management meeting.
But then I said, come on, we're doing project planning. And I said, look, I'm absolutely fed up with projects that are guaranteed to succeed. Where are all the projects? Can't we just do 10 projects that are guaranteed to fail? and then I said, if you do projects that are guaranteed to succeed, they're going to be horribly conservative things.
Yes.
So you've got to just do things that that's just fun stuff.
Just what most people want.
And all the management said, yes, that's a really good idea. Yeah. And guess what they did?
Yeah.
Nothing.
Yeah. And
so they never did any projects.
So
that were guaranteed
my
to fail.
aphorism for that is everybody loves change except for the change part.
So the other thing you must have thought carefully about the titles of your talks, because
Sure.
it's almost a provocative one. The Uppsala 1997 keynote, I thought very nice. The computer revolution hasn't happened, which I thought was nice, because you're talking to a lot of people who think the computer revolution has happened, and here you are saying it hasn't happened. So it's a nice, catchy title.
Yeah, exactly.
And then you're into that, and you
and even when it does happen, we should keep saying it.
Yeah. I wonder when it'll happen. That hasn't happened yet, but.
It's like the human. When does civilization happen?
So there's a bonk. There's a. I don't know if it was planned, but there was, for me, a bonk me on the head moment when you said every object should have a URL.
Oh yeah.
And you'd already said that objects are like little servers.
Yeah. I think the thing is, once you think biology.
Yes, of course.
It's trivial. That's why I say I don't take any credit for these ideas. I just woke up because I'd seen these ideas over and over again, and the thing I hadn't realized was the level of power they had.
So in preparation for this, I was watching some of your lectures, and
I can't stand to watch them.
No, so that was bonk me in the head moment, and I thought, yes, I shall immediately, because I'd said on the Erlang mailing list, so I posted this and said, so every Erlang process in the universe should be addressable and introspective, and we should all talk to these.
Yeah.
So I expected that there would be a great enthusiastic response, and everybody would immediately stop what they were doing to implement this, because having implemented everything else would be easier.
Yeah.
And guess what?
Yeah.
They didn't.
Yeah.
Why don't they do it?
Well, because
it's very strange.
So
why don't you go out and do this stuff? I told you yesterday. Make everything remotely controllable.
You have no idea how close a thing it was for personal computing and the internet. Because you have to realize that the Mansfield Amendment in the early 70s from the Vietnam War shut down ARPA to an enormous degree. Xerox PARC only was put together because Taylor wanted to finish off the previous 8 years. And if he hadn't done that, the critical mass wouldn't have been funded to get to, a practical Alto personal computer and a practical Ethernet and a practical internet.
Because
it wouldn't have happened.
That there are these things.
Try doing that. How about today? Suppose there wasn't an internet today. This is years later, right? But think about, hey, guess what? We're going to do something where we don't get to control it. There's going to be no central control. It's going to have 10 or maybe even as many as 100 billion nodes on the thing. It's going to be self-balancing. We have to be able to change everything in it while it's running because we don't get to stop it. It has to be like biology. And most engineers just check out there but why do we do it? Well, partly because the original funder, Licklider, known as Lick, who's a psychologist, in 1963 wrote a memo to the members of the Intergalactic Computing Network. And somebody asked him, why do you call it the Intergalactic Network? He says, well, engineers always give you the minimum. I want a network that covers everything on Earth, and so I'm asking for an intergalactic one. And when the engineers scale it down, we might get it. But in that memo, one other thing that's important about reading that 1963 memo, it came out of an experience that he had, which he was a psychologist. He was used to the computing at MIT, and he was out on one of these enormous Sage computers. When I say enormous, I'm talking 2 software pitches of vacuum tubes. That's big. And they had the first time-sharing terminals, and he was sitting down doing something, and he wanted to run a statistical package that, well, he was in Jovial, and they didn't have it. He said, well, this computer is connected by telephone to the computers at MIT. They didn't have the ARPANET yet, but they had that. And he said, I've got a package in Fortran there that I could use. And they said, well, you can't do that.
So I have
let me just finish the story. And so this little story was in there. But basically what he said, look, if we actually succeed in building the intergalactic computing network, our main problem is going to be learning how to communicate with aliens. And he didn't just mean with other people. He meant between us and software at the other end of the world, and software computing with software at the other. So every form of communications mode between active entities was going to be like communicating with aliens, because there would be far, far less basis for common ground. And how do you solve that? So we took that to account. That was a real help in getting the internet to turn out the way it was, because we were doing something much smaller than what Licklider wanted. We only did TCP/IP. We didn't do what the thing needed, which was to make consistent objects across the internet. This has been done since, but it's not deployed on the internet in a standard way as a layer to TCP/IP. So there was a huge stop once TCP/IP was successful, and people have done almost nothing with it except use a few local, even Google uses only a few hundreds of thousands to millions of computers. That's nothing compared to 10 billions or so. So my complaint would be most computer people, A, think way too much like their first programming course, which was almost certainly in algorithms and data structures, and that set of ideas do not scale at all. Forget about them. And the second thing is most computer people think about the scale of things that they're working in now or had been working in, and they have no sense of scaling. So computer people have been unable to take care of Moore's law. And third, computer people don't care about, like if you saw a sketchpad from 1963 done by one guy as a PhD thesis, that's like the greatest thing single thing done in our field because it has every part of most of what we want. It's got simulation, it's got modeling, it's got programming that can't go wrong. What's great, it doesn't use a theorem prover. It actually uses an engineering theory, so it has tolerance on the solutions. It doesn't require exact. I mean, the ideas in this thing, you could do a dozen projects starting now, and they'd be hailed as revolutionary. So, you know, my general thing when I talk to university students is, hey, get off your asses and learn something. You know, nobody asked you to become a computer person, but if you're going to be one, try and think more like a real scientist rather than just some, you know,
Well, I
pissant
think
engineer.
I mean, I started off as a physicist, and so you know,
Yeah.
when I'm dimensioning things, I say, so how many, you know, I ask people, how many atoms are there on the Earth? Well, it's 10 to the 50, you know, so I mean, can you just number and name every atom on the Earth? Well, that'll probably be good enough. Or do you want to name every Planck volume of the universe or something?
Yeah.
And then dimension it. And if you dimension it for that, then it's going to work fine, you know, and then you can scale it down to 1 or 2 people. If you start with 1 or 2 people and try and scale it up, then you're going to have
Yeah,
problems.
exactly. Scaling, I mean, scaling isn't the only thing,
No.
but man, it is big.
Yeah.
It is a big thing to hook in, to think about the scaling aspects even before you're trying to solve your problem.
And also,
Because
I
time
mean, I
passes.
think computing people, I just say, just don't break the laws of physics in your programs. I mean, there's no such thing as simultaneity. You know, there's rays of light bouncing backwards and forwards, electrons bouncing up and down, and photons hitting things, and you have to be aware of that. You can't just pretend that we can have simultaneous knowledge of data in 2 different
Dick
places.
Feynman
It's not true.
Dick Feynman was once in my pool, and we were admiring the sunlight on the water and the waves, and he said, "Isn't it just wonderful that what we're seeing is the superposition of a gazillion different messages off the side, and it just looks so chaotic, and yet with the right little detectors, which we can make with a little float and a little spring and a little weight, we can just pick out one frequency. I mean, it's just the most wonderful superposition of enormous numbers of things, and what does it mean to separate out and isolate, and what does linear and nonlinear mean? These are the things that really help get from where we are now into something that actually has some life to it, rather than just being a legacy anchor.
So I was thinking in a conference like this, the normal format of the conference is people, they say, well, they had some problem, and then they've used some technique to solve the problem, and then they describe the solution to the problem in great detail and forget to tell you what the problem is. And we don't take the opportunity to talk about problems that are unsolved. So
Usually the problems are boring, too, because they are picked up too easily. You know, an easy problem that you recognize is too much in the current
so I think
context.
in 1900, David Hilbert defined,
Yes,
came out with 23
the
problems
23 problems.
that hadn't been solved. And in one conference he was in Paris somewhere, he came out with 10 of them.
Yeah.
So what problems do you think what problems should we be looking at? What are the most important unsolved problems that we should work on?
Again, slogans, it's not big data, it's big meaning. There's a slogan. So one of the ways of doing this kind of thinking, like I say, you're in a different world. You have to get out of the practical world for a second. You have to get into extremism, crazy world. So crazy world is, you know, the idea fixe of I'm going to be a monomaniac on something. And, you know, and suppose I'm just extremely sensitive and in pain. That is one of the sensations that people like me have, basically pain. And trying to find the sources of the pain. So a simple one is this wonderful thing about language, which also should help people understand about language. Every sentence you can make up in English, you can also toss a not in there. And so even a simple natural language like English is bigger than the universe. You can say things that aren't there, and this should bring home, Einstein said, to the extent that mathematics gets at truth, it does not get at reality, and to the extent it gets at reality, it does not get at truth. He understood the complete difference between the two and the problems of using a symbol system for something that isn't like the symbol system in any important way. Many scientists get confused on this because they tend to think of the math as the reality, and it's absolutely not. So to me, the first thing is, let's just negate everything. Let's write down the top 50 things. This would be a good thing if we had this thing at the beginning of this conference, which I was kind of hoping, because it would give people something to do here. That, like, write down the top 25 beliefs in computing, and then put a knot in front of them and see what that is. Just the hell of it. Big data. Not big data. Well, if it's not big data, what is it? Well, big meaning. Of course, it has to be about meaning. The problem is the big data people are confusing some of the means to the end as an end. And this happens all the time in computing. We turn the sub-problems into the problems because we get mired in the sub-problems. So just going through the things that you personally believe. I do this maybe every 3 to 5 years. I sit down, spend a week writing down things I think I believe, and I spend a fair amount of time trying to see whether there's any reasonable reason to believe them still. Some of them I have, like I mentioned the situations, actions, and causal laws thing because I think McCarthy was getting at one of the prime cruxes in computing, which is that you want to be able to advance state and you need to do it absolutely safely. So you'd like to be able to reason perfectly about how you're going to advance the state, and you'd like to organize the system so you get the best of both worlds. Monads is too much of a kludge. That's trying to save functions and missing what McCarthy had already gotten to more than 50 years ago. So that kind of stuff drives me crazy. It really does. It's like, where did you people come from? How blind can you be? Why are you treating this like a religion? Well, Bob Barton, the great computer designer, when I had him as a professor, and one of the things he used to say was, systems programmers are high priests of a low cult. Think about that. So he had a.
The other thing I kind of worries me is I get the impression that an awful lot of the things we have are done because we can do them, not because there's any need for it.
I call that inverse vandalism. It's making things because you can.
It has unpredictable side effects and consequences. So one of the things that worries me is this silly idea of the cloud, and just, you know, if we just store everything in the cloud, the unintentional side effect of that is we'll probably lose all our history. And I'm kind of worried, like, in 200 years' time, we'll look back and say, oh, sorry, we just lost the history of the 20th century.
Another guy
I'm wondering, of all these things...
Invite Vint Cerf here next year and talk, because Vint is very, very concerned about this.
I'm very concerned
and has been doing a fair amount to try...
So what I wanted to ask you were I think losing history, I think hijacking our attention systems by bombarding us with crap.
Yeah.
Of these things, which do you think are the most dangerous? Which should we address first?
Well,
we kind of rank them in order of severity we can knock off the bad ones first.
So I had the unsettling, 2 days ago I had tea with a young Oxford professor of philosophy, nice guy, and somewhere in the middle of it, I mentioned Francis Bacon's Four Idols, from this book he wrote called in English, it's The New Organization of Science, Nova Morgana, 1620. He'd never read a word of Bacon. This is the philosophical structure that underpinned the actual invention of science, which really happened here in England, because scientists don't give you science. It's something like the Royal Society that gives you science, because science needs other people to debug. You have to have a social system in order to debug your ideas. It's not enough just to have it. So Archimedes was a great scientist, but the Greeks didn't have science. They didn't have the thing. And Bacon pointed out in this book a lot of things, but one of the things he said, look, the simplest way to think about us humans is we are born with bad brains. And our bad brains are partly because of genetics. Our bad thinking is partly because of genetics, partly because of our culture, partly because our languages are terrible at representing what we want to have as ideas, and we have academia that's constantly recycling bad ideas into the young. And he said, what we need, he said in this book, is a set of heuristics for getting around our bad brains. That's what his definition of science was. It wasn't just to find out what forces might keep the moon in the sky and the planets around the sun. No. What Bacon saw science is as a set of methods for thinking more clearly in the best ways that we know how. So when you think of it that way, that should be the center of any schooling system in the 21st century. And it certainly should be a big part of any kind of schooling system for people who are doing technology, which because of the Industrial Revolution, we can do this inverse vandalism of making something and spreading it by the billions. And the problem is our nervous systems are overwhelmed by things that seem to be an environment. We start accommodating to total environmental things like television and the internet. So I dare say most people in computing are not at all aware of this stuff, never have read a word of McLuhan, have not looked at cognitive psychology, couldn't design a user interface to save their ass, or any of these things. So what we've got is what I think is to me, one of the most beautiful things that humans have come up with. I just love computers. And B, we've got basically a know-nothing culture who's trying to do things with the computers. It's just too ad hoc. It's like if you wanted to be a physicist in the Middle Ages, you only had to get a pointed hat.
So it struck me,
because they didn't know anything.
The last time we spoke, we had this very nice conversation.
It was simpler. There wasn't an audience.
Yeah, there weren't people there. And just as you left, we started talking about Douglas Adams, and I didn't know you'd worked with Douglas.
Great
and then I
fan.
thought, well, Douglas Adams, he came up with like the Babel fish and things like this. You stick it in your ear, and I was thinking, do we need computer people to figure out what we're going to do? Because half of the thing, this Internet of Things, Douglas would have loved this, all these completely stupid things that people are coming up with.
Yeah.
And sensible things like a Babel fish. So what was your relationship with Douglas?
Well,
was he funny?
Douglas and I got along, we met a long, long time ago when somebody told him, did you know The Hitchhiker's Guide to the Galaxy is kind of like Alan Kay's Dynabook? And so he got interested in, by the way, if you don't know the story, Douglas was quite a drinker, and so was I back in those days. And one evening, he'd had a ton. He was a big, huge guy. He's like 6'5", 6'6", really nice. And he just sort of wandered out in Cambridge and fell asleep in one of the greens out there. And he woke up in the middle of the night not knowing where he was, looking up, and there are all these stars up there. And a phrase popped into his head, Hitchhiker's Guide to the Galaxy. He didn't know what that meant. But he started thinking about what.
So he would have loved the Babel. I mean, there is a Babel fish in almost.
Well, what's interesting is that, so Douglas and I, my wife and I used to stay at his home when we were here. He used to stay at our home. He and his daughter came for dinner just 2 weeks before he died suddenly. Terrible thing. He had played basketball. He didn't feel well, went to a doctor. The doctor said, you're okay. Didn't test him. Next day he was dead. 49 years old. That was bad. Really bad. And the thing about, here's what McLuhan said. He said, look, most people think they live in reality. They're completely unaware that everything they do is completely conditioned by what they believe about the world. This is easy to prove to people, but most people short circuit. It's actually part of what Buddhism is about. is this distinction between efficiency and what's actually going on. And so the problem there is that when you are aware of what's going on, you can see the present as kind of a construction. It could have been a bunch of different ways. And McLuhan said most people can't see this at all. And so people, as his phrase was, people are driving faster and faster into the future, but steering only by looking in the rearview mirror. That's a beautiful one. Because they assume that the present is some form of reality. But he said artists can see the present for construction. That is what they were reporting in their art. Great artists are all, look at what Guernica is, just to take something relatively recently, but they're seeing what is actually going on because they have this pain. Their pain comes from reacting to what's actually going on, and artists are people who have to report that to people. But the cool thing about artists, and Douglas is one of these, is, and Douglas did have a lot of pain from this stuff, but what a person like this does is if you can see the present as a construction, you can have much better ideas about the future, because what is an idea that isn't incremental? An idea is escape from the context you're in. Well, what is a joke? A joke is taking you down one context and revealing you're in another. So the simplest form of a creative act is a joke. What is a discovery? In science, it's looking at the same world that you saw up to a second ago, and all of a sudden you see some relationship that was right in front of your nose. It's a joke. You start laughing. What is art? Art is the reminder that our brain is so limited we can hardly deal with even getting from one moment to the next. And art forces us to realize there's more there. And Kessler, who wrote a book called The Art of Creation, The Act of Creation, I'll commend it to you, pointed out the emotional reactions to jokes is ha-ha, to science is aha, to art is ah. And each one of them is a different kind of emotional discharge you get from escaping from the context that you, for a few seconds ago, you thought was reality. So what I believe, and Douglas's idea was if you want to communicate with anybody, of course, it takes a special person to do it. His idea was always do it with humor.
Yeah, sure.
So like the most bitter book he ever wrote was called The Last Chance to See. It was still quite funny, but it was basically about how we're killing off species and how unique each of the species is. It's actually a plea. But he wanted to get people to the end of the book. And so his theory of writing a polemic, or Kurt Vonnegut.
Vonnegut.
Every book that Kurt Vonnegut wrote was an attempt to deal with the fact that he had been a prisoner of war of the Germans in the firebombing of Dresden, which far more people died than in Hiroshima. It was one of the worst things we did it, the British and the Americans. We incinerated 300,000 people by just making a conflagration. Vonnegut had to clean it up.
So now we've got we've built these billions of computers, and it strikes me we're doing all these stupid things.
Maybe we shouldn't have.
We do, on the other hand, have severe environmental problems and things, and we do need to plan the usage of our resources using these things. So in fact, there are. I collect sort of good news stories, because there's so many bad news stories. People with Parkinson's disease. Somebody made a spoon that when your hand shakes, it's got a little accelerometer and a little computer, so it shakes in the opposite direction. These are brilliant devices.
Yeah, sure.
So why aren't we building these things instead?
Well, they're like these, right? This was one of the first declarations that biology is not destiny. That's what human beings are about. Biology is some of our destiny, but it isn't all of our destiny, and it's up to us to figure out what to do with the part that we can't change biologically, and a lot of that is through education. From the ideals of the people who are my heroes, and I didn't talk about Engelbart, and I didn't talk about many of the people I talk about in longer talks. Well, Engelbart had been in World War II, and his thought was, man, the world is in a complete fucking mess. And particularly after the German concentration camp, people were sick about this. And Engelbart was, I guess, 19 or 20, and he decided to dedicate his life to helping humanity. And eventually this turned into realizing, just as you say, that a lot of things that have positive effects can be done by people working together, and the computer should allow people not just work by themselves, but to actually coordinate large plant, because we can simulate things, we can deal with threats and everything else. These were the ideals of the 60s that were the mother's milk for graduate students like me. Well, guess what? It happened. It just didn't happen to the general public. Virtually everything being done in science and engineering today is just like what we thought it was going to be for the whole world, but only the scientists and the engineers took it over. Almost no scientific thing is done today without having things that are far, far beyond classical mathematics. They're nonlinear models of very, very complex structures. Similarly in engineering, bridges used to collapse, like the Tacoma Narrows Bridge, one of my favorites.
So Francesco is kind of making signs, which I think he thinks that the guys here might want to have a beer or something like that.
I thought you'd learned how to ignore those signs. I'm not even looking in that direction.
So I think perhaps we should draw it to an end.
Yes, I have a dinner party I have to go to, but I would, we're here now.
So I'd just like to thank you for coming.
You're welcome. It's a pleasure. Thank you.